Hello, welcome to our Semiconductor education program. I'm Vincent Chang. We're going to continue our learning on the subject of analog integrated circuit bias and focusing on understanding the foundation of the current mirror and the current source, part 2, base-compensated. Let's start with our conclusion from part 1. This is the effect. We kind of figured out the effect of finite current gain is a negative impact on the current mirror. What's the impact? The imperfect is non-ideal transfer ratio. If beta is 100, let's say the left-hand side is 1 million, what the right-hand side is going to be? It's going to be 0.98 million, 2% loss. So here's the key concept. Why 2%? Why the error term is 2 over beta? Where the 2 over beta originally comes from? From base, right? So therefore the error, remember, when you think about the time you analyzed this before. IC over beta, IC over beta, 2 IC over beta, 2 over beta, 2 IC over beta, 2 over beta. Therefore, if you can understand this, you can send the error term 2 over beta, 2 over beta, 2 IC over beta into an emitter. And from the emitter to base, it has to be divided another 1 plus beta. You got the concept? This is the fundamental concept to suppress the error, the error caused by the base current. So it's called base current compensation technique. Base current compensation technique. If you don't quite understand what I just said, because I was leading you based on kind of intuitive analysis, kind of intuition. If you cannot follow me on this, let me explain step by step. First of all, you have to find out the reference current, the VCC. Deduct 2 VB, the first one, VB3, and then VB1. And the leftover voltage across the R, get the reference current. The reference current, this is what I just said, 2 IC over beta, right? And then from emitter to base, it has to be divided another 1 plus beta like this. Take the node, pay attention to the node X. Based on the node X, you will find out the relationship between IO and the I reference. But to this point, probably you already figured out the answer. The left-hand side is what we mentioned before, 2 over beta. What about the right-hand side? Blue corresponds to the blue. Blue corresponds to the blue. The blue on the left-hand side is 2 over beta. You can take out the IC. The same thing with the question mark on the right-hand side. You can simply take the blue base current, 2, and take out the IC, divided by beta square plus beta, and plug in like this. Got it? It's approximately equal to. The exact solution should be beta square plus beta. But beta square is much higher than beta. Beta is negligible. If you're still struggling to establish maybe a little bit doubt, then the last resort is to do the KCL, to do the circuit analysis. The reference current, based on the KCL, apply the KCL on X, the node X. Then you have the flow in the left hand side, and flow out, the sum of flow out, IC plus this. And then it's this. Because IC equals IO. I reference divided by IO. This is what I just said. The error term is 2 over beta squared plus beta. Then you get this. Current transfer ratio. So what's the concept behind this? Number one, what's the concept behind this? Base compensated. Use the third bipolar transistor and send the error current to the third bipolar transistor Q3 and take and suppress the error current to compensate the error base current compensation. That's the concept behind this. So what's the result? 2 over 100 could become 2 over 10,000. 2 over 100, 2% could become 0.02%. The error is almost negligible, can be negligible. The current can be almost the same, 1 milliamp and 1 milliamp. That's the concept. That's the takeaway of this lecture. Again, 2% on the left-hand side. Now, the error is 0.02%. This is the technique called base-compensated current mirror. I hope you got the key concept of this lecture video. Thanks for watching.